Minimization of circuits using Karnaugh maps. So when we say that we want to minimize a Boolean function, this basically is just a procedure where we're going to produce Boolean sums of Boolean products that would represent the Boolean function with the fewest products of literals, such that in a way where this product contains the fewest literals possible among all sums of products that represent a Boolean function. Okay, basically minimizing a Boolean function will allow us to create a circuit that would use the fewest gates and the fewest inputs possible, which would give us a more efficient and even a cheaper circuit when we are going to create or design a circuit. And that's what we really want, right? We want to be efficient. We want for things to be cheap if it's possible. So minimization of Boolean function can be done by using Karnaugh maps. Okay, a Karnaugh map is basically a graphical method, and it's also sometimes called as K-map, K for the Karnaugh, that will allow us to find terms to combine for a Boolean function involving a relatively small number of variables. There are 4 possible mean terms in the sum of products expansion of a Boolean function with variables x and y. You could verify it on our right, where you could see here a map. Okay, a K-map for a Boolean function in these 2 variables consists of 4 cells. Okay, x and x complement for the rows, and y complement for the columns. And each intersection of this row and column represent one mean term. Okay, for the first cell, for the upper left, we have xy. For the upper right, we have xy prime or xy complement. And then on the lower left, we have x prime x complement y, and the complement of x times the complement of y. Okay, we would put a 1 in the cell to represent a mean term if this mean term is present in the expansion. Okay, the cells are said to be adjacent if the mean terms that they represent differ in exactly 1 literal. Okay, we have here an example. We need to find or construct the K-map for A, B, and C. Okay, for A, let us draw the K-map. The K-map for 2 variables is 2 rows and 2 columns, right? Where the columns are our y and y prime or y complement. Here we have x and x prime. Okay, now if this is the expansion, we have x, y, and x complement y. Okay, we would have to put a 1 on the cell. Okay, so we have xy, so that's here, that's the intersection of xy and the intersection of x prime y. Okay, so that's the K-map for letter A. The K-map for letter B, again, we will draw the map. Okay, here is the complement y and the y complement. Okay, for letter B, we have the mean term x complement y. Complement of x and y intersection is here, and here we have xy complement and xy complement combination, or sorry, intersection is found here. For letter C, we have 3, so we are expected to see 3 ones on our K-map to represent the 3 mean terms. Okay, we have x complement y, y complement. Okay, so x complement y intersection is found here, so that's 1 for this cell. xy prime is here. Oops, sorry. For the first mean term x prime y, that's here. The second mean term xy prime is the one on the upper right. And the last mean term that we have for this Boolean sum is the x complement y complement. So that's this one. So these are the K-maps for A, B, and C. Now, we want to simplify the sum of products and expansions given in example 1. So these were our answer in the example 1, right? Now, for K-map, for us to use K-map to minimize our circuit, we have to do this. the first thing that we have to do is group our ones together. Okay, group our ones together in such a way that you would only have 2, 4, 8, 16 ones. So the first rule in K-map grouping, when you want to group the ones, is that you could only group ones with in 2 raised to n. Okay, 2 raised to n. So these values are 2, 4, 8, 16. Okay, so we want to group the min terms or the ones in our K-map. Either you have 2 ones, 4 ones, 8 ones, or 16 ones. The second rule, this is the first rule. The second rule for grouping of min terms, or when we want to simplify the sum of products expansion, is that you could only group adjacent ones. It means to say that they are beside each other. Okay, beside each other. So group only adjacent ones. For letter A, we only have 2 ones, and that's the largest group that we could make, and both ones are adjacent to each other, so this is already one group. Okay, for letter B, since they are not adjacent to each other, right, these ones are not adjacent to each other, so that's just singular. There's really no group of ones that we could make here. But for letter C, there are 2 group of ones that we could make. Alright, this is one group, this is also one group of 2, 4, 8, 16 ones. Again, we have to make a group of ones. First group that we have to make is the largest number of ones possible, but in this case we only have 2, right? That's the largest possible group that we could have. Okay, and after grouping this K-map, therefore we could simplify, and the way we could easily simplify using K-map is when remember, there is an identity, or there is a law where the sum of x and its complement is equal to 1, right? This is a law that you have discussed in the class already. Okay, you have to recall this law, that the sum of a variable or Boolean variable and its complement is equal to 1. Therefore, here, since we have x and x prime in this group, that automatically is 1, and 1 times y would just give us an expression of y. Okay, so for letter A, the simplification of the sum of products is just y. For letter B, since there is no adjacent ones, therefore the sum x prime y plus xy prime is its simplest form already. Okay, now here we'll go back to this again. If the variable and its complement is found in the group, that would automatically give us a 1. So in this case, we have here for this group x and x prime. So this, we would only have left y prime. Okay, and for this group we have y and y prime, therefore we only have left is x prime, or complement of x. Now, since we have 2 group of ones, what we have to do is we have to add these groups together. So the answer for letter C, so the final answer for the simplification of the sum of products expansion of letter C is x complement plus y complement. Okay? Okay. Now, what if we have three variables in our K map? If we have three variables, then we would have um, this K map here where we have two rows of four columns. Okay, two cells are said to be adjacent if the min terms that they represent differ again in exactly one literal. Here, we could fold the K maps. So we could say that this column here is adjacent to this column here. Okay, as you could see in figure B. So x, y prime z is adjacent to x, y, z, and vice versa for the second row. Now here are blocks in K-maps, or the groups of 1 that we could make. If we have a 1 for the corner, then this is already one group. Okay, if we have, say, a 1 here and a 1 here, that is also one group of or one blocking in K-map that we could make because it's adjacent, right? Okay, so here we have 4 adjacent ones, and here we have, what if all of the cells have 1? Then that's just one big block, because this is still 8, right? And again, we could only group ones with with 2 raised to n, and 2 raised to 3 is equal to 8. Therefore, we could have a block with 8 ones. This is possible. Okay, now let's work on this blocks. If y and z, x, y prime, z prime has a 1, and x prime, y prime, z prime has a 1, then this is just represented by y prime, z prime. Again, why is it y prime, z prime? Because x and x prime is found in this block. And again, if you have the variable and its prime on one block, then we could do away with that literal. Okay, here if we have ones on the corners, x prime y z and x prime y prime z, again we have here y and y prime in one block of ones, right? Since we have y and y prime, we could do away with y, and we would only be left with x prime z. That's why this expansion here is represented by this simplification that we have here. The same thing goes if we have this block of ones here. You would have the complement of x, so we could do away with the literal x, and we could also do away with the literal of y, because we have y and y complement in this block of 1, and we are left only with the z prime literal. Okay, here we have ones in a row. This block, what are the literals that has its complement? We have here y, and we also have z and z prime. So we could do away with y and z literals, and we are only left with x prime. If all of the cells have 1, then this just means that we have all the literals, x and its complement, y and its complement, z and its complement, and that would give us 1 plus 1 plus 1, and the sum of ones is equal to 1. That's why we have 1 as the simplification of this Boolean sum of Boolean products that we have on the right side of our equal sign. And that is how blocks in K-maps in 3 variables are used. Now we have here an example where we would apply that concept of blockings in K-maps with 3 variables. We want to use K-map to minimize the sum of product expansions. We have here A and we have here B. Now for A, we need to draw the K-map. Okay, here we have a K-map of 4 cells. 4 columns with 2 rows. Here we have x, and here we have x complement. And going back, you would see yz prime, okay, yz prime, y prime z prime, and y prime z. Now we have to put a ones for each of this mean term that we have here. So x y prime z is here. X y prime z prime is the intersection here. X prime y z is this one here. X prime y prime z is here, and x prime y prime z prime is here. Now we have to group our ones. The first thing that we have to do is group a 1, the largest group possible. So 4 ones here is one group, so that's one group, and all ones must be grouped. Okay, all ones must be grouped. So if we have here a 1, we still have to make a group for this, and again we have to group it in 2 raised to n in the largest way possible. And again, remember that the cells are adjacent, right? This row, this column here is adjacent to this column here. That's why we could group this one with this one here. So we have 2 groups, and now let's find the representation of this group, the simplification of this group here. So what are the literals that have its complement? We have x and x prime, so we expect to have no x in our mean term. And here we have z prime and z, so we could also do away with z prime and z. Now we are left with just y prime. So this block of 4 ones here is just equal to y prime. Now let's go into this second group that we have here. We have the complement of z and z, so we would do away with z, and we are left with x and y prime. So this block here is represented by x prime, y prime, and since we have 2 groups, we have to add them together. That is x prime y prime plus y prime. Now let's do an answer letter B. Again, we have to have the K map of 4 columns and 2 rows. So the columns here are yz, y prime z prime, yz prime, y prime z prime, and y prime z. The rows are represented as x and x prime. Doing the same thing, we have to put a 1 for each of the mean term that we have here. We have xyz, xyz prime, xy prime z, and xy prime z prime, x prime yz, that's here, x prime y prime z, that's here, and x prime y prime z prime, which is here. So how could we group this? Again, we have to group this in a way where we would have the largest group possible. So this is one group. Okay, that's one group. This is also one group, the adjacent ones, and this is one group for this one here. So for the adjacent one, since we have y and y prime, we also have x and x prime, so that's just gonna leave us with z. For this chunk here of ones, we have x and x prime, and we also have z and z prime, so that will leave us with just y prime. And for this group of 1 here, we would have the complement of z and z prime. We have z and the complement of z. We also have y and the complement of y. That's why we are left with just x. So for this b, we have x, y prime, z, and we have to add them all up together. Therefore, we would have a simplification of that Boolean sum of products as x plus y prime plus z. And that is how you do Karnaugh maps in 3 variables.